The purpose of this video is to introduce the concept of center of mass and to present a few examples to show how to use a formula to find the center of mass. The center of mass is defined as the average position of the matter in a body or a system. Let's take a look at this traffic cone and think about where the center of mass might be. You'll notice that the cone is symmetric about the vertical axis, and it seems obvious that the average position of the matter is somewhere along that line, but where is it exactly along the line? Well, the middle of the cone is somewhere in here, but the cone gets wider and heavier toward the bottom, so the center of mass must be further down. Eventually, we'll need a method for finding the center of mass of such an object, and that's going to involve some calculus. But before we get to that, there are lots of examples that don't involve calculus, and looking at those will help to give you a sense of what the center of mass is all about. So let's look at the following example. 3 objects are placed on a table. Where is the center of mass, or the average position of the matter in this system? The equation we use to find the center of mass is this one, and you can see that it is in fact what we refer to as a weighted average. Each of the x's in the equation refers to the position of one of the masses. Each of the small m's refers to the mass of one of the individual masses, and the capital M stands for the total mass of the system. So let's go ahead and use this equation. First of all, we need to choose an origin, and I'm going to choose the center of mass of the apple as my x equals 0 point, or my origin. So I should mention here that I could choose anything at all as an origin, and the center of mass equation will always output a value that is relative to that origin. So based on the origin I have chosen, I'm going to make up some other positions for the other 2 masses. And I also need to have some masses provided here. And I'm just about ready to go. I just want to mention one last thing before I proceed, and that is that you may have noticed that the mass of each of these objects is not located all at a single point. So for example, the apple is an extended mass itself, and it's not all of the mass in the apple is located right at x equals 0. And as it turns out, it's perfectly reasonable when using this equation to pretend that for each of the individual masses, all of the mass in one of those individual masses is located at the center of mass of the object. And I'll show you the proof of this in a later video, but for now, you're probably willing to believe that this is true. So those yellow dots represent the center of mass, center of masses of each of the individual objects. So let's go ahead and plug in some values here. The first entry inside the parentheses represents the apple, and then the silver ball is shown, and then the orange. And when you do that calculation, you find that the center of mass is at 0.4 meters, which is right about here. So the center of mass seems to be a little bit to the left of center. That makes sense since the apple and the silver ball are over there on the left-hand side. And it's also worth noting that the center of mass does not need to be physically on any of the mass in the system. So here it's a point out in empty space between the various objects. All right, so let's take a look at another example. This time we will look at a 2-dimensional grid with 3 objects on the grid. And this time, when we find the center of mass, it's going to be an ordered pair. There's going to be an x position for the center of mass and a y position for the center of mass. So we're going to say that each square on the grid is 1 meter by 1 meter, and we'll say that the origin is right at the center of the grid. And the question is, where is the center of mass of the system? So we have the equation from the previous problem that will help us to find the position, the x position of the center of mass. And we're just going to replace all of the x's with y's in the equation, and that will provide us with a way of finding the y coordinate of the center of mass. Before you jump into the calculations, you can ask where generally the center of mass will be. I bet that you can come up with an argument, either conceptual or mathematical, that it should be somewhere in this region. So when we get an answer, it had better be somewhere within that gray zone. Let's begin with the x direction. We're going to plug in the various masses along with the x coordinates of their positions to find the x coordinate of the center of mass. Notice that since the pink dot is to the left of the origin, its x coordinate is negative. That -3 in there is the x coordinate of the pink dot. And it's important to get those signs right in order to get the right final answer. So the x coordinate of the center of mass is -1.28 meters. And so that's right there. So the center of mass is somewhere along that blue dotted line. Let's do the same thing to find the y coordinate of the center of mass. And at this point, you could stop the video and try this on your own, and then you can use the video to check your work if you want to. So this is the equation that you get after you make your substitutions. And here's the result. So the y position of the center of mass is at -0.29 meters, which is right here. And so that red X represents the position of the center of mass for this set of objects. And you can see that it is indeed in the gray region, and it's closer to the pink object, which is the most massive one in the system. And so that seems like a reasonable result. So now you have seen how to find the center of mass for a system of particles. But how would you find the center of mass for an extended object like the traffic cone? Well, in the next video, I'll show you how to use calculus to find the center of mass of an extended object. And then this is a calculation you should be able to do on your own.